Picture this. On a cool morning, the airplane lifts off quickly and climbs with ease. By contrast, on a hot, humid afternoon, the same aircraft uses more runway, takes longer to accelerate, and climbs less efficiently. In aviation, changes in air temperature, humidity, and pressure directly affect performance. Pilots use calculations, equations, and tools like density altitude charts or calculators to predict how their aircraft will behave. Today, we'll be going over density altitude, what it is, how to calculate it, and why it's so important for pilots to understand. Before we begin, be sure to like this video and subscribe for more aviation tips and insights from Epic Flight Academy. Let's get started. Density altitude is pressure altitude corrected for non-standard temperature. In simpler terms, it's the altitude that the airplane feels it is flying in. When air is dense, there are more air molecules, especially oxygen, packed into each cubic foot of space. That means the wings have more molecules to create lift, the propeller has more to push against creating more thrust, and the engine has more oxygen to burn fuel efficiently, creating more power. When air is less dense, the opposite happens. Lift decreases, propellers have less air to bite into, creating less thrust, and engines lose power because they aren't getting as much oxygen. Pilots often compare true altitude with density altitude to understand this effect. For example, an airport 5,000 feet above sea level may feel more like 10,000 feet on a hot, humid day. On the ground, the airplane will perform as though it were flying at 10,000 feet, not 5,000 feet, the true altitude. As the aircraft climbs, the density altitude increases as well, further reducing performance. This is why calculating density altitude is so critical for safe flight. To best understand how a pilot can determine the density altitude, first they must understand the following definitions and terms. True altitude is an aircraft's actual height above mean sea level. Pressure altitude is the altitude corrected for standard pressure, which is 29.92 inches of mercury. Outside air temperature is the actual temperature of the air where you are flying. And standard atmosphere temperature is the temperature that would normally be expected at a given altitude according to the International Standard Atmosphere Model. After understanding these definitions, the next step is learning how to calculate the pressure and density altitude. Pilots can convert pressure altitude into density altitude using this simple formula. For example, if an airport is at a true altitude of 5,000 feet mean sea level, and the current barometric pressure is 30.02 inches of mercury, the pilot can subtract 29.92 from 30.02 equaling 0.1. Then multiply 0.1 by 1,000, which equals 100. Add 100 to 5,000 and you get a pressure altitude of 5,100 feet. This will now be used to find the density altitude. Density altitude equals pressure altitude plus the outside air temperature minus the standard atmospheric temperature times 120. When the outside air temperature is warmer than the standard atmosphere temperature, the air becomes less dense. Subtracting the standard value from the actual temperature shows how far conditions are from normal. Multiplying that difference by 120 gives you a correction in feet. Adding that number to the pressure altitude gives you the density altitude. For example, imagine you are at an airport with a pressure altitude of 5,100 feet. At that altitude, the standard atmosphere temperature is 5 degrees Celsius. On this day, the outside air temperature is 20 degrees Celsius, which is 15 degrees warmer than standard. Multiply 15 by 120 and you get 1,800. Add that to the original 5,000 feet, and the density altitude is 6,900 feet. In practice, this means the airplane will perform as though it is taking off in air from nearly 7,000 feet, not 5,000. That results in less lift, less engine power, and a longer takeoff roll. Now that we understand what density altitude means and how to calculate it, let's see how it plays out in real conditions. Here is a comparison between Centennial, Colorado and New Smyrna Beach, Florida. Centennial already sits high above sea level, so the air is thinner to begin with. On hot, humid days, density altitude can reach 10,000 feet. That means an airplane performs as though it's at 10,000 feet, not 5,885 feet. Even a 7,000-foot runway may not be enough, so pilots often fly early, late, or wait for cooler weather. Even sea-level airports can feel higher. On muggy afternoons, density altitude can rise by 2,000 feet, so a runway just above sea level can suddenly perform like one at 2,000 feet. Although density altitude may be high at both airports, it's important to understand that as it approaches the aircraft's service ceiling, the point where climb performance drops to about 100 feet per minute in propeller aircraft, or 500 feet per minute in jets, overall performance begins to suffer significantly. Pilots must calculate density altitude to ensure their aircraft can perform safely, with enough runway for takeoff and sufficient climb performance to clear surrounding terrain. The International Standard Atmosphere sets sea level temperature at 15 degrees Celsius or 59 degrees Fahrenheit, and it decreases about 2 degrees Celsius for every 1,000 feet of altitude. At 5,885 feet, the standard is 5 degrees Celsius or 41 degrees Fahrenheit. If the actual temperature is 30 degrees Celsius or 85 degrees Fahrenheit, the density altitude rises to about 8,000 feet. That's why we say density altitude is the altitude the airplane feels like it's flying. The relationship between air density and performance is not just academic, it's practical. Every pilot must understand how to calculate density altitude and recognize its effect on flight. Whether you use a table, chart, or electronic calculator, the goal is the same. Compare actual conditions with the standard atmosphere and see how they change your aircraft's capabilities. This allows pilots to make go or no-go decisions and ensures their passengers and crew are safe. As density altitude rises, true airspeed increases for the same indicated airspeed. Drag reduces lift, and engines lose power. Knowing how to compute and apply these numbers keeps aviation safe. Understanding density altitude can mean the difference between a safe flight and one that pushes your aircraft to its limits. Thanks for watching. If you learned something new, make sure you like this video and subscribe for more aviation tips and insights from Epic Flight Academy.